Light takes 8 minutes to travel from the sun to Earth. That means everything we see in the sky is already in the past. Even the nearest star is not quite what it seems. Not in this moment. It is what it was. That idea is simple. Measurable is also profound. It means that when we look outward, we look backward. Every photon that reaches us is a silent witness from a different time. A cosmic delay is stitched into the very act of seeing. This delay is not trivial. A star 100 light-years away sent its light before the first electronic computers existed. Some galaxies shine from distances so great, their light began the journey long before our solar system formed. These aren't poetic metaphors. They are testaments to the scale of time and space we exist within. We see the present in our hands, but the sky shows us what is gone. A telescope is a time machine pointed up. Distances in kilometers collapse under the weight of this cosmic scale. What is 100 million kilometers to the sun when the nearest galaxy lies millions of light years beyond that? Traditional units become absurdly small. So we surrender them. Instead, we count in time seconds, hours, years of light. 1 light second is 300,000 kilometers. 1 light year is nearly 10 trillion kilometers. Our Earth, rotating and tilting modestly in its orbit, is wrapped in a bubble of delayed information. We do not see space, we see ancient signals. Yet with this simple conversion of distance into time, a remarkable clarity emerges. To say a galaxy is 10 million light-years away is to say we are witnessing it 10 million years ago. With every step farther outward, the universe reveals more of its youth. It's like peering through layers of sediment where deeper means older, and older means stranger. This is not just a scientific reality, it is a narrative structure written into the fabric of the universe. The farther you look, the more primal the story becomes. Even the scale of our own solar system, which seems vast, folds quickly under cosmic perspective. Light takes mere hours to cross from end to end, touching Pluto's orbit in about 10 hours. But then, to reach even the next star years, to leap to the stars beyond that centuries of light travel. Our Milky Way contains hundreds of billions of stars, each separated by spaces so wide the nearest neighbors are measured in parsecs, a unit born from trigonometric subtlety. Hold up a finger at arm's length, close one eye, then switch. The finger jumps. That is parallax. The change in perspective from 2 viewpoints. Astronomers use Earth's orbit as the arm's length, 1 astronomical unit wide. A nearby star seen in June will appear in a slightly different position 6 months later. From this shift, and the angle it creates, they calculate the distance. This method works well for stars a few hundred light years away. Beyond that, the angle becomes too small. The stars sit too still. So astronomers reach for brightness. A nearby star's absolute brightness, known from parallax, becomes a candle to compare with more distant, similar stars. The dimmer a match appears, the farther it must be. But the light weakens with distance not linearly, but by the square twice as far is 4 times as faint. The universe does not give up its depth easily. Every measure is an inference. Every distance is reverse engineered from delay, dimness, and distortion. Beyond our galaxy, more galaxies float, millions of them. They form clusters and superclusters, stretching across the cosmos like veins in stone. Each is a swirling storm of stars, billions strong. These galaxies are not merely far, they are ancient. Their light began before life ever stirred on Earth. The space between galaxies makes even the vastness of the Milky Way seem intimate. Yet, within our own corner, stars show their secrets. Many are not solitary. They are paired, even tripled gravitational families orbiting one another in long, slow dances. Binary systems are common, and they vary wildly. Some stars orbit each other leisurely over decades. Others spin so closely they exchange matter, heat, and energy, shifting form and character over time. The sky is not quiet. It is teeming with motion, with evolution, with competition. The average distance between stars, about 1 parsec, is an enormous gulf. That's 20 million times the diameter of our sun. So despite the dazzling number of stars in the sky, they are scattered thinly across space, each lonely in its sphere, but their variety is endless. Stars differ in color, brightness, mass, and age. Their color reveals their temperature, and their brightness hides a story of size, heat, and internal fury. And imagine a star not as a point of light but as a globe of gas, suspended in nothing, held together by gravity and aglow with nuclear fire. The cooler stars burn red, the hotter ones, blue-white. Their placement in the Hertzsprung-Russell diagram, a map of stellar characteristics, traces a path from dim red dwarfs to blistering blue giants. The sun sits among the yellow-white, a modest beacon with a surface temperature of nearly 6,000 Kelvin. It is neither young nor old, neither large nor small, and yet the sun is the threshold. It is the standard by which others are judged. We speak of solar masses, solar luminosities. In that framework, some stars blaze with the force of 10,000 suns, others, white dwarfs and red dwarfs, whisper with faint, dying light. Some have surfaces as hot as 25,000 Kelvin, others linger near the threshold of fusion, barely radiating. A few are mere ghosts dense, dim remnants cooling over eons. The universe permits this diversity. It breeds it, encourages it, then watches as stars live, compete, and die. What we see in the sky is not static. It is history. It is rivalry. It is the consequence of physics unrolling across billions of years. And every glimpse we catch is shaped by the most fundamental truth of all: we are always looking into the past. The light that reaches us carries more than distance and delay. Encoded in every wave and photon is the temperament of the star that created it, its temperature, its rhythm, its weight. Most stars radiate steadily, but some flicker and swell like living hearts. These variable stars pulse in brightness, their outer layers expanding and contracting in cosmic breaths. The rhythm is not random. It is precise, often tied directly to a star's intrinsic brightness. Measure the pulse, and you know the power. Measure the power, and you know the distance. This relationship, first discovered by Henrietta Leavitt in the early 20th century, gave astronomers a tool as elegant as it is powerful. The longer a variable star's pulsation, the more luminous it is. By comparing that true luminosity with how dim it appears from Earth, we can measure its distance. These stars, called Cepheids, are among our most reliable beacons. They populate our galaxy and others, blazing like lighthouses across the sea of space. Some, like Polaris, throb gently, others vary more wildly, but each is a metronome in the dark, ticking out the depth of the cosmos. These Cepheids are not mere curiosities. They are evolved giants, larger and more massive than the sun, nearing the end of their stellar lives. Their luminosity is tremendous, often thousands of times that of the sun. They have passed through earlier stages of fusion, consuming hydrogen and now oscillating as their internal structures search for equilibrium. In these fluctuations, they sing, their surfaces ripple, their cores heave. The starlight flickers, but not in chaos. It flickers with the precision of a clock built in fire. Deeper inside the stars, away from surface rhythms, something more intimate occurs. A balance is constantly being negotiated. Gravity pulls inward, pressure pushes outward. For a star to exist, it must strike a perfect truce between collapse and explosion. The inner heat provides the pressure. That heat comes from nuclear reactions. Without them, the gravity would win. The star would fall in on itself and disappear. In the core of our sun, the temperature reaches 15 million Kelvin. The pressure is so intense that gas behaves unlike any we experience on Earth. It is plasma fully ionized, with atoms stripped of their electrons. The particles move with furious speed, crashing into one another, generating radiation not in gentle visible light, but in harsh X-rays. That radiation does not stream freely to the surface. It is trapped, scattered, absorbed, and re-emitted endlessly, taking millions of years to escape. The light we see from the sun today began its journey long before the first humans walked upright. This is not metaphor. It is delay built into the sun's anatomy. The photons that finally emerge have bounced 1 trillion times through a crowded furnace of plasma. Only when they reach the convective outer layers can energy rise more swiftly, carried upward by boiling gas currents like water in a pot. In smaller stars, convection dominates. In larger ones, radiation carries more of the load. But in every case, the star finds a way to ferry its energy from core to surface and then into space. This energy flow is not silent. Inside the star, pressure waves move sound. In a sense, though not in air, these acoustic waves reflect and refract, creating complex standing patterns. Each star is a resonating chamber, humming with its own voice. In the sun, these vibrations tell us about the interior we cannot see. Helioseismology, the study of solar sound, reveals the shape of its core, the depths of its convective zone, and the hidden churn of its layers. The sun is not still. It rings like a bell. It hisses like steam. And those sounds, though silent to us, drive physical changes across its atmosphere. The outermost layers, known as the corona, are paradoxically hotter than the surface below, 1 million degrees or more, heated by the chaotic flow of sound and magnetism. The thinness of the corona prevents it from radiating its heat away. Instead, it explodes outward, carried by charged particles in what we call the solar wind. This stream of gas flows through the solar system, shaping planetary atmospheres, buffeting magnetic fields, and whispering to every satellite and probe. Other stars possess their own stellar winds, some gentle, others savage. A few are so intense they tear the stars apart over time. Gas flows away in rivers, accelerated by radiation and magnetism. In some stars, the shedding is slow and sorrowful. In others, it is a tempest. The universe does not mandate serenity. Some stars live like monks. Others die in flames. Yet all of them are powered by the same fundamental engine, nuclear fusion. At its heart, a star is a reactor. It fuses hydrogen into helium, converting mass into energy. But this process is not simple. Protons are positively charged. They repel each other. To fuse, they must come unimaginably close. Even in the center of the sun, with temperatures soaring and particles speeding, most collisions do nothing. Only occasionally 1 in a trillion does quantum tunneling allow a proton to sneak past the barrier, to touch, to fuse. This is the first of 2 great hang-ups. The second is subtler. Even when 2 protons meet and bond, they must transform. 1 proton must become a neutron. This requires a weak nuclear interaction, an unlikely quantum event. On average, a proton in the sun's core waits billions of years to undergo this change. But there are so many protons that some are always reacting, keeping the fire alive. Fusion releases energy because the helium nucleus that results is slightly less massive than the 4 protons that formed it. The missing mass becomes energy, flung outward as heat and light. The process is known as the proton-proton chain. In larger stars, a more complex cycle dominates the carbon-nitrogen-oxygen cycle, or CNO. It is less dependent on quantum chance and more efficient at higher temperatures, but all fusion in stars has the same goal: transform mass into energy, and in doing so, resist collapse. The stars are not static. They are not simple. They are delicate balancing acts, held between gravity and radiation, between collapse and expansion. They are ancient engines wrapped in fire, whispering across the cosmos through light and sound. And yet, even they have lifetimes. Their fuel is not infinite. Their patience runs out. And when it does, something else begins. A star's death begins in silence. Its core, having spent millions or billions of years transmuting hydrogen into helium, reaches a point of exhaustion. The fire wanes not everywhere, but in the heart where fusion once blazed cleanly and steadily. What remains is a cinder of helium, hot and inert. The outer layers, still glowing, still shedding light, no longer draw energy from within. The balance tilts. Gravity, ever patient, resumes its slow encroachment. The core contracts. In falling inward, it releases gravitational energy, heating the surrounding layers. A shell of hydrogen outside the core begins to burn, reigniting in a fury that pushes the outer envelope outward. The star swells, its surface cools. It becomes a red giant. The transformation is not immediate, but when it comes, it is dramatic. A star that once shone with a steady yellow-white glow now glows red and vast. It becomes luminous not by raising its temperature but by expanding its surface. It is no longer a quiet main-sequence star. It is bloated, unstable, nearing the end. For lower-mass stars, those similar to or smaller than the Sun, this is the final phase of grandeur. The core, composed of helium, contracts further. When the temperature crosses 100 million Kelvin, helium ignites in a flash. Not an explosion, but a rapid runaway fusion event. Helium fuses into carbon and oxygen. The flash stabilizes the core for a time. A new balance is struck. The red giant stabilizes, if only briefly. The envelope is now tenuous. A strong stellar wind builds, driven by both radiation and pressure. The star begins to shed its outer layers. Shells of gas drift away into space, lit by the remaining core like lanterns in mist. What remains is a white dwarf, a naked core, hot and small, about the size of Earth. It no longer burns fuel, it merely cools, radiating away the last heat of its long life. The white dwarf is dense. A teaspoon of it would weigh tons. And yet it shines, dimly, for billions of years. The Sun will become such a relic. In 5 billion years, our star will cast off its atmosphere and rest as a pale white ember, glowing faintly in the twilight of time. But for stars with greater mass, the ending is far more violent. They burn through hydrogen quickly, then helium, then heavier elements. The core becomes layered, like an onion, each shell fusing a different element. Carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. With each new fusion process, the temperature and pressure rise. But there is a limit. Iron is that limit. Fusing iron does not release energy, it consumes it. When the core fills with iron, the engine stalls. The outward pressure of radiation disappears. Nothing holds gravity back. Collapse begins. The core falls inward in milliseconds. Electrons are crushed into protons, forming neutrons. The matter becomes incompressible. The collapse halts abruptly, and the rebound sends a shockwave outward. In that instant, neutrinos, those ghost-like particles, pour out in vast numbers, carrying away energy. The shockwave, assisted by this sudden flood, tears through the star, blowing off its outer layers in a colossal detonation, a supernova. For a brief time, the star outshines its entire galaxy. A supernova near Earth would cast shadows at night. It would be as bright as the full moon. The explosion spreads heavy elements, carbon, oxygen, gold, uranium into space. These are the seeds of new stars, new planets, and eventually, new life. We are built from this wreckage. The iron in our blood, the calcium in our bones, the carbon in our cells, all forged in stellar death. What remains after such an explosion depends on the mass that was left behind. If the remnant is less than about 3 times the mass of the Sun, the core stabilizes as a neutron star. Imagine a city-sized sphere, 10 kilometers across, denser than anything else in the universe apart from black holes. A thimble of neutron star matter would outweigh a mountain. The surface gravity is so immense that any object dropped from a centimeter above would strike with the force of a bomb. Neutron stars often spin rapidly, their magnetic fields sweeping through space. These rotating beacons are called pulsars. With each turn, they emit a pulse of radiation like the beam of a lighthouse. Some spin hundreds of times per second, a blur of dense matter trapped in an eternal twirl. But if the remnant is more massive still, not even neutron degeneracy pressure can halt the collapse. The core continues falling. There is no force in nature strong enough to stop it. The result is a black hole. This is not just an object. It is a boundary in space and time. Beyond the event horizon, nothing escapes, not light, not sound, not thought. The core collapses into a point of infinite density, a singularity. Around it, space is warped beyond comprehension. Time itself slows as you approach. To fall into a black hole is to vanish from the universe's visible story. Your final light stretched and reddened until it fades into silence. Black holes do not roam freely, devouring stars at random. They obey gravity like any other mass. But when they do feed, the process is spectacular. Matter spirals inward, heating to millions of degrees, emitting X-rays and gamma rays. In some cases, vast jets erupt from the poles, carving cavities in the interstellar medium. The feeding is not quiet. It is theatrical, violent, luminous, beyond understanding. The star is gone. The fusion is over. But its legacy persists in the debris scattered across light years, in the elements scattered through future generations of stars, in the silent core that endures as neutron star or black hole. Every galaxy is shaped by such events. Every planet owes its material to the ghosts of long-dead suns. A star's life is long and quiet. Its death is brief and cataclysmic. And in that ending, the seeds of new worlds are born. In the darkness between the stars, clouds of gas drift silently, great volumes of hydrogen and helium, tinged with traces of heavier elements. For eons, they remain quiet, cold, featureless. But within these vast expanses, gravity begins its slow, relentless whisper. Slight imbalances, perhaps triggered by a passing shockwave from an ancient supernova or the subtle tug of a neighboring cloud, set particles into motion. Denser regions collapse inward, drawing in more mass. The process accelerates. The cloud fragments. Each fragment forms a rotating globule, an embryo of a future star. These protostars, cloaked in veils of dust, cannot yet be seen in visible light. They glow faintly in infrared, heat building as gravity compresses their hearts. The core tightens, pressure climbs, temperature rises. But for millions of years, there is no fusion. The heat is gravitational, a furnace built on falling. As the protostar contracts, it begins to spin faster. This is not by choice, but by law. Angular momentum conserved as mass collapses. The spinning disk around the protostar flattens and spreads, forming the stage for the next act, the birth of planets. Within the disk, dust grains coalesce. Minute collisions build larger clumps. The game is not fair. The biggest grow faster, drawing in smaller bodies. What begins as scattered dust becomes a chaos of tumbling rock and ice, each fragment following its own orbit, some spiraling inward, others flung outward. Over time, gravitational dance favors the few. Planetary embryos emerge, planetesimals the size of mountains, then continents. Some collide and shatter, others merge. Those that endure become protoplanets, their paths more circular, their mass sufficient to shape themselves into spheres. Gas giants form farther out, where cold temperatures allow volatile gases to condense. These massive worlds draw in hydrogen and helium, growing rapidly, their cores cloaked in deep atmospheres, closer to the star, where heat drives gases away. Terrestrial planets remain barren, rocky, fragile. In the heart of the system, the protostar finally reaches the threshold. Its core crosses 10 million Kelvin. Hydrogen ignites. Fusion begins. A balance is struck, the inward pull of gravity matched by the outward push of energy. The star is born. The sun awakens. Its fierce light sweeps away the remnants of the gaseous cloud, pushing back against the birth materials that formed it. The radiation and solar wind clear out debris, shaping the remaining architecture of the system. The planets that survive do so at the whim of this stellar tantrum, and their fate is sealed in the geometry of their orbits. In the early chaos, impacts are frequent. The inner solar system becomes a battlefield. Asteroids and comets bombard the young Earth. Some bring water, others sterilize the surface with fire. The scars remain in cratered moons, in tilted axes, in odd orbital resonances. A late, great impact tears a chunk from Earth's side. The debris coalesces into a satellite, the Moon. Its presence stabilizes Earth's rotation, sets tides in motion, and locks our planet into a rhythm that will nurture future life. After a few 100 million years, the bombardment slows, the solar system settles, the planets spin quietly in their orbits, moons circle planets, and the sun shines with steady brilliance. But the sun is not still. Its surface roils with convection. Magnetic storms arc into space. The solar wind continues, an eternal gale of charged particles streaming outward, touching every planet and pressing against the interstellar void. The sun's light takes 8 minutes to reach Earth. The signals we receive from its surface are already history. What we see is not what is, it is what was. This delay in light is not unique to our star. It is the universal consequence of speed and distance. Every point in the sky is a museum of the past. The farther we look, the older the image. A galaxy 10 million light-years away appears as it was 10 million years ago. We are surrounded not by objects in the present, but by echoes, fossils of light. Distance and time are entwined. To observe deeply is to peer into history. A telescope is a time machine, and the night sky is a window into moments that have long since passed. The nearest stars are light years away. Their parallax, the slight shift in apparent position as Earth moves around the sun, gives us a measure of their distance. Beyond a few hundred light years, even this shift is imperceptible. We must rely on luminosity, color, and spectral fingerprint to guess their remoteness. The stars themselves vary immensely. Some are red dwarfs, dim and enduring, destined to burn for trillions of years. Others are massive blue giants, burning so hot and fast they perish within a few million years. Most stars, like the sun, are main sequence, a band on the Hertz-Sprung Russell diagram that reveals a simple truth: a star's mass determines its fate. The diagram itself is no mere chart. It is a map of stellar life, from the dim and cool to the hot and brilliant. It lays out the stellar population in patterns that hint at hidden laws. The main sequence, the red giants, the white dwarfs, each region tells a story, not just of temperature and brightness, but of origin and destiny. The stars are not randomly placed. They cluster, drift in families, rotate around galactic centers. Many are not solitary. Binary systems are common: two stars locked in orbit, some distant, others so close they transfer mass, their evolution intertwined. Some binaries merge, igniting new flares of energy. Others erupt in nova or end in shared collapse. In rare cases, one devours the other. Their stories are many. Their silence conceals the violence beneath. What we call a star is a process, not a product. A balance of forces, a furnace of nuclear fire, a beacon that writes its own biography in light. Each flicker across the night sky is a whisper from a distant forge, a statement of physics, chance, and endurance. And each of these whispers arrives late, trailing behind the moment of its making, forever separated from the now by the span of space and time. Inside the quiet skeleton of a dying star, the fire of creation meets its limits. Hydrogen, once abundant and obedient, is long gone from the core. Helium, too, has fused into heavier elements: carbon, oxygen, silicon. What remains is a complex, layered relic, like an onion of atomic ancestry, each shell burning a different fuel, each closer to collapse than the last. The fusion reactions, which once staved off gravity, now accelerate with desperation. In the final days, a massive star can burn through silicon in mere hours, producing iron, a dead end in nuclear alchemy. Iron neither gives nor takes energy through fusion. It is inert, the ash of the stellar flame. The core grows heavy with it. Its weight, no longer countered by outward pressure, begins to pull inward, faster than sound can escape, faster than the atom can respond. The iron heart collapses. Electrons slam into protons, forming neutrons. In an instant, a city-sized core becomes a neutron star. Above it, layers of gas fall inward like a city crushed by gravity. But the core resists. The infall halts, rebounds. An enormous shockwave bursts outward, ignited by a flood of neutrinos, the ghost particles of the universe pouring from the newborn neutron core in numbers beyond comprehension. The star explodes. A supernova lights the galaxy, outshining billions of suns. Its brilliance lasts only weeks. But in that moment, it sears itself into the cosmos. The elements forged in its interior: gold, uranium, iodine scatter into space. Dust enriched by the dead becomes the seeds of the living. The remnants of the star vary by mass. If the core is under the limit, about 3 times the sun's mass, it settles as a neutron star. A thimbleful of its matter outweighs mountains. Its magnetic field is 1 trillion times stronger than Earth's. It may rotate hundreds of times per second, sending pulses of radiation across space, a lighthouse in the void. We call them pulsars, these trembling fossils. They speak not in words, but in timing perfect, mechanical, mournful. Each beat carries memory. Each signal is the echo of collapse held in exquisite rhythm. But if the core is heavier still, even neutrons are crushed. Nothing can resist the final fall. Space itself curves inward. Light cannot escape, and the star becomes invisible, a black hole. This term, so soft in sound, masks what it means. A black hole is not a thing, but a boundary. A cliff in space-time beyond which no return is possible. It is a wound in the structure of reality, the place where time stops making sense. Surrounding the black hole is the event horizon, the point of no return. Outside it, time moves forward. Inside, all futures lead to the singularity, a place where density becomes infinite and physics loses its voice. We do not know what lies at the singularity. Our equations scream with infinities and contradictions. General relativity bends. Quantum mechanics fractures. It is the edge of knowledge, the end of prediction. Black holes grow by swallowing. They devour stars, gas clouds, other black holes. At galactic centers, they sit like monarchs, invisible yet ruling. Some weigh millions or billions of solar masses. Their gravity sculpts the movement of stars, shapes galaxies, triggers jets of matter and energy that stretch across intergalactic space. They are silent architects of cosmic order, formed in violence, living in shadow. And yet, not all end in collapse. Lesser stars walk gentler paths. If born with low mass, they shine steadily for tens of billions of years, fusing hydrogen slowly, living longer than the current age of the universe. When their hydrogen is gone, they swell into red giants, shed their outer layers into space, and settle as white dwarfs. These stellar embers, roughly Earth-sized, glow faintly for eons. Some may eventually cool into black dwarfs. Though the universe is still too young to have produced any, they are the final breath of stars too small to die with thunder. In some binary systems, white dwarfs steal matter from a companion. When enough accumulates, a thermonuclear runaway occurs. The star explodes in a Type Ia supernova so consistent in brightness that it serves as a cosmic milepost, measuring the universe's expansion. There are other signals of distance, too, Cepheid variables, massive stars that pulse rhythmically, grow brighter and dimmer over predictable cycles. Their period tells us their true luminosity. Comparing this to their apparent brightness reveals how far away they are. Light, again, is the courier of truth. Our knowledge of the universe is built from what arrives on waves of light and particles of ghostly origin. Neutrinos from supernovae, gravitational ripples from colliding black holes, shadows cast by galaxies, spectra of starlight. Even the silent vacuum speaks. The cosmic microwave background relic radiation from the birth of the universe saturates space. A whisper from 13 billion years ago. Its pattern tells us the shape of space, the fate of time, the balance of matter and dark energy. And so we orbit, this Earth spinning beneath a star that will someday swell, burn its hydrogen to helium, shed its skin, and leave behind a white dwarf. Long after we are gone, it will remain, dimming slowly. Around it may still circle the ghost of what was a system shaped by violence and decay, but also by balance, emergence, and radiance. The universe, for all its harshness, is not a place of pure entropy. It is a realm where structure can rise from chaos, where time does not just erode but reveals. Every star carries a story written in heat and pressure, forged in collapse and light. Every planet is a testimony to improbable assembly, a relic of gravitational games. And every life that gazes skyward becomes part of this unfolding epic, finite, fragile, yet curiously aware of the infinite beyond. In the cold spaces between galaxies, in the dark hearts of dying stars, in the minute reactions of subatomic particles, there are echoes, not just of matter and energy, but of questions, of silence interrupted by light, of time made visible. The story never ends. It only fades beyond the horizon, into the vastness from which it came.
Or are some of those tiny lights the remnants of dead stars whispering the final chapters of stellar evolution? Could one of them be something even more extraordinary? A fossil from the dawn of time, a survivor of the universe's first fire. Look up. On a moonless night, the stars stretch across the sky in quiet splendor. We trace their patterns like ancient skywatchers once did, linking point to point, imagining heroes, beasts, and gods. But the truth is far more intricate than the constellations we draw. To the unaided eye, stars appear uniform, tiny fixed lights, distinguished only by the shapes we impose upon them. Yet behind this illusion of sameness lies a cosmic hierarchy, where stars are sorted not by myth but by mass lifespan and elemental ancestry. With powerful telescopes and centuries of astrophysical insight, we can now rearrange the heavens not by story but by science. And when we do something astonishing, becomes clear, some stars are as common as dust, while others are rarer than gold. Let us embark on a tour of stellar rarity. A cosmic census that begins not with the brilliant giants, but with the silent failures. At the bottom of the stellar ladder are the brown dwarfs, stars that never truly ignited. With masses under 8% that of our sun, they are too light to spark the hydrogen fusion that powers true stars. These protostellar almost drift cold and dim, scattered like cosmic shadows through the Milky Way. For every star that burns, there may be another that tried and failed. The galaxy is littered with them. Next come the stars that did succeed, those now basking in the main sequence, the stable core burning phase that defines 90% of the stars in our galaxy. Our sun is among them, a yellow dwarf, modestly bright and relatively rare. Only 7% of stars fall into this category. Far more common are the red dwarfs, cooler, dimmer, and longer lived, comprising a full 75% of all stars. Quiet and unassuming, these stellar workhorses may be the cradles of countless uncharted worlds. As we move up, the ladder of mass stars become not only brighter, but exponentially rarer. White supergiants like Canopus blaze brilliantly across vast distances, yet make up less than 1% of the galactic population. More extreme still are the hypergiant stars, like Stephenson 2D18, whose bloated envelopes bleed mass at staggering rates, shedding material equivalent to Jupiter in single gusts of stellar wind. These giants grow and unravel in tandem, barely clinging to existence. But not all stars burn through their fuel in steady calm, some near the end of their lives in far more violent or fragile ways. Stars like our sun will eventually swell into red giants only to slough off their outer layers and leave behind a white dwarf, a hot, dense core that no longer shines by fusion, but by memory. These compact remnants already account for about 5% of stars we see today, and in time, as stellar birth slows and deaths accumulate, they will come to dominate the galaxy. For the more massive stars, the finale is explosive. They collapse under their own gravity, releasing supernovae so powerful they briefly outshine entire galaxies. What remains are the most exotic stellar forms we know: neutron stars and black holes. Neutron stars, just a dozen kilometers wide, but heavier than the sun, spin rapidly emitting radio pulses like celestial lighthouses. The rarest among them are the magnetars, whose magnetic fields are 1,000 trillion times stronger than Earth's starquakes ripple across their crusts, releasing gamma-ray bursts with energy no human structure could withstand, quakes that would register over 23 on the Richter scale. And yet even these titans are not the rarest stars. To find the rarest, we must look deeper, not in space, but in time. At the very beginning of the stellar story, long before the Earth formed and before any heavy elements existed, the universe kindled its first lights. These were the population 3 stars, massive, brilliant, and ephemeral. Born in a cosmos of pure hydrogen and helium, they lived for only a few million years, but in that time, they sowed the seeds of all chemical complexity to come. They are the ancestors of every star, planet, and living thing. And though none have yet been seen, some astronomers believe a few may still exist, relics in the shadows waiting to be found. If we could detect even one, it would be like discovering a living trilobite, a breathing relic of the cosmic dawn. So the next time you trace a shape across the sky, know this: behind each point of light is a story. Some are ordinary, others are ancient. A few are unimaginably rare, but all of them in their own way are part of the same cosmic tapestry, and the stars, it turns out, are not equal at all. Hot planets, a spectral revolution. When we look back through the lens of mythology, we often find the sun portrayed as divine, an eternal provider of light, warmth, and order. In Japanese legend, Amaterasu, the radiant goddess of the sun, withdraws into a cave in sorrow, plunging the world into darkness. It is only through the laughter of the other gods that she is coaxed back, returning light to the sky. This symbolic reverence for the sun underscores an ancient truth. Without it, life on Earth would be impossible. Yet the modern view of the sun and of stars in general has evolved far beyond mythology. Stars are not divine beings, but physical objects. Giant spheres of incandescent plasma bound by gravity, powered by nuclear fusion, and governed by the laws of quantum mechanics and thermodynamics. And to understand them, we need not rely on stories, but on spectra. Our earliest tools were the naked eye and speculation. Then came telescopes pioneered by Galileo, revealing that what once seemed like points of light were often binary systems or entire galaxies. But the true revolution came not from magnification, but from decomposition, from the ability to break light into its component wavelengths and study the absorption patterns within. Every atom and molecule absorbs light at specific wavelengths, a quantum fingerprint imprinted on the spectrum of any light it interacts with. These gaps, called absorption lines, appear when electrons within atoms jump to higher energy states, absorbing photons with exactly the right energy. And since the energy of a photon is directly related to its wavelength, each missing line tells us not only which element is present, but also something about the physical conditions within the star, especially its temperature. In the 1860s, Italian astronomer Angelo Secchi began sorting stars based on their color and spectral characteristics. He found that red stars were cooler and blue stars were hotter, a thermodynamic rainbow mapped onto the night sky. But Secchi's system was only the beginning. A few decades later, a group of women at the Harvard College Observatory, derisively referred to as computers, took the work further. Among them were Williamina Fleming and Annie Jump Cannon, who laboriously examined thousands of glass photographic plates, assigning spectral classifications to tens of thousands of stars. They created a taxonomy that persists to this day. The sequence, organized by decreasing temperature, was originally alphabetical, but was restructured once scientists understood that temperature, not simply the presence or absence of certain lines, was the fundamental organizing principle. For a time, planets were still considered part of this sequence, a misconception born from focusing solely on elemental presence rather than abundance. The Sun contains the same elements as Earth: carbon, oxygen, iron. But it was not until 1925 that the real breakthrough came. Cecilia Payne, a British-born astronomer working at Harvard, performed a detailed analysis of the Sun's spectrum by taking into account the ionization states of elements and the physical principles of quantum mechanics and thermodynamics. She demonstrated that the Sun, and by extension most stars, was composed almost entirely of hydrogen, with a small fraction of helium and trace amounts of heavier elements. The Earth was no longer simply a cold star. Stars and planets were shown to be fundamentally different, not in kind, but in proportion. Unfortunately, Payne's thesis was initially rejected, seen as too radical for the time. It was only after independent confirmation years later that her work gained the recognition it deserved. Her discovery marked the end of the idea that stars were merely hot planets. They were instead revealed as unique entities in their own right, nuclear furnaces that convert mass into energy through fusion, illuminating the universe. But the story did not end with the chemical separation of stars and planets. In the 1940s, astronomer Walter Baade noticed another intriguing pattern. Not all stars were created equal, even among stars. There were differences in chemical composition. Baade observed that stars in the galactic halo regions devoid of star formation showed significantly fewer heavy elements than stars in the galactic disk, where new stars were being born. This difference in metallicity suggested that the halo stars were older born in a time when the universe had not yet enriched itself with successive generations of stellar nucleosynthesis. Baade coined two categories: population 1 stars rich in metals and population 2 stars poor in them. Our Sun is a population Y star forged from gas that had already been enriched by previous generations of stellar death population 2 stars. By contrast, are ancient relics, older, simpler, and purer. But even these stars were not entirely devoid of heavy elements, and that led to one final tantalizing question: could there be stars out there formed before any supernova? Before carbon, before oxygen, before even iron? These would be the true primordial stars, composed almost entirely of hydrogen and helium, the only elements forged in the crucible of the Big Bang itself. Such stars, if they exist, are known as population 3 stars. They would be the first generation, the spark that lit the cosmic night. Born in a pristine universe, their existence would bridge the gap between cosmology and stellar astrophysics. Yet none have ever been directly observed. They lived fast and died young, likely exploding as supernovae within a few million years, too distant, too brief, and too obscured to be detected by current telescopes. And yet their legacy remains. Every atom heavier than helium, every drop of water, every molecule of DNA, every grain of dust is a descendant of those first stars. Their death seeded the cosmos with the ingredients for everything that followed. The search for these elusive population 3 stars continues, and with it our quest to understand the birth of the elements, the formation of galaxies, and the origins of life itself. For in the light of stars we read the history of the universe and perhaps our own. Population 3, the first stars. What if we could look far enough into the night sky to witness not just the ancient light of stars long extinguished, but the very birth of starlight itself? What if buried in the deep red glow of the cosmic past, we could find the ancestral giants that first broke the eternal darkness, the celestial titans that forged the very seeds of complexity? In 2022, we may have come closer than ever before. While combing through deep sky images captured by the Hubble Space Telescope, a team from Johns Hopkins University encountered a cosmic anomaly. Among the hazy distant galaxies, those smudges of stretched light billions of years in transit, was a pinprick of brilliance unusually isolated from the amorphous background glow. It was improbably a single star. The astronomers named it Earendel, from the Old English word meaning morning star, a poetic reference to its ancient light that may have dawned when the universe itself was just beginning to wake. Based on its luminosity and spectral characteristics, Earendel was estimated to be between 50 and 100 times the mass of our Sun, and with a surface temperature exceeding 20,000 Kelvin. It was over 3 times hotter than our familiar solar companion. Ordinarily, stars at such distances would be far too faint to resolve individually. But in this case, the universe had offered a rare assist, a gravitational lens. This natural lensing effect is a consequence of general relativity. Massive clusters of galaxies warp the very fabric of space-time, bending the path of light emitted from objects behind them. When alignment is just right, this light is magnified sometimes by factors of hundreds or even thousands. It was through such a lens that Earendel's host galaxy had been stretched into a giant arc, and the light of this one distant star was amplified to the point of visibility. Gravitational lensing is not new. It was first predicted by Einstein in the early 20th century and later confirmed observationally, but the precision alignment required to magnify a single star is astronomically rare. That this happened at all is nothing short of cosmic luck. Yet the real surprise lay not only in the discovery of a star so distant, but in the color of its light. Due to the universe's ongoing expansion, light from distant galaxies is redshifted, its wavelength stretched, its energy diminished. As it travels across the expanding fabric of space-time, the farther the source, the greater the redshift. Earendel's light was astonishingly redshifted, indicating that it had been emitted just 900 million years after the Big Bang, meaning its photons had been traveling for over 13 billion years before arriving at our telescopes. This placed Earendel in a time close to what we believe is the era of the first stars, population 3. But what became of Earendel? Despite its light surviving the ages, the star itself is almost certainly long gone. A star's fate is governed by a single defining trait: mass. Mass determines a star's temperature, its luminosity, and most crucially, its lifespan. Stars like our Sun are middleweights massive enough to sustain hydrogen fusion in their cores, but not so massive as to live violently or die young. When the hydrogen in a Sun-like star's core is exhausted, fusion continues in surrounding shells, while the core contracts, heating up and triggering helium fusion. The star swells into a red giant before eventually shedding its outer layers into a planetary nebula, leaving behind a dense, inert white dwarf composed primarily of carbon and oxygen. These white dwarfs can persist for billions, perhaps trillions of years. But for more massive stars, the story ends with far more violence. Stars above about 10 solar masses experience successive stages of fusion, burning heavier and heavier elements in concentric shells. Ultimately, they reach iron, the fusion of which consumes energy rather than releases it. Without a fresh source of outward pressure, gravity takes over. The result is a supernova, a cataclysmic explosion that tears the star apart, sending enriched material flying into the interstellar medium. The core collapses into a neutron star, or if massive enough, a black hole, a region of space-time from which not even light can escape. And paradoxically, the more massive the star, the shorter its lifespan. These giants live fast, burning through their fuel at breakneck speed, their enormous energy output a sign not of endurance, but of fragility. While our sun is expected to endure for around 10 billion years, a 100 solar mass star may live for only a few million mere cosmic moments. So Arundel, brilliant as it was, will have lived and died in a blaze of elemental violence, but it is the products of that death-heavy elements that make Arundel's story so critical to our understanding of the cosmos. It was in the 1940s that astronomer Walter Baade proposed that not all stars are created equal. He observed subtle differences in stellar spectra between stars located in different regions of the Milky Way. Those in the spiral arm sites of ongoing star formation exhibited higher levels of heavy elements. Baade labeled these stars Population 1, the youngest generation enriched by the deaths of their ancestors. In contrast, stars found in the halo of the galaxy, those in globular clusters or drifting in the intergalactic outskirts, showed much lower metallicity. These older stars, dubbed Population 2, formed earlier in cosmic history from gas that had experienced less recycling through stellar deaths. But this raised a deeper question. If even Population 2 stars contained trace amounts of heavy elements, then there must have been a time before any such enrichment. A time when the universe was a clean slate composed almost entirely of hydrogen and helium, with just the faintest whisper of lithium and beryllium created during Big Bang nucleosynthesis. Theoretically, there must have been a first generation of stars. Stars formed before any enrichment forged from pristine cosmic gas clouds. These are the elusive Population 3 stars. Despite decades of searching, no Population 3 star has yet been conclusively observed. Arundel's light, while ancient, still seems to bear the spectral fingerprints of some heavy elements, suggesting it is likely a Population 2 star. But what makes Population 3 so hard to find? The conditions of the early universe were drastically different from today. In modern star-forming regions like the Orion Nebula, heavy elements are abundant. These metals, through their electron configurations, enable gas clouds to cool efficiently by radiating away energy in the form of photons. This cooling is essential. It allows clouds to condense under gravity, forming dense cores that can ignite fusion. In the primordial universe, however, there were no heavy elements to assist in this cooling. Without metals, early gas clouds retained their heat, more stubbornly resisting collapse unless they were enormous. Only the most massive clouds, those with sufficient gravitational pressure, could overcome this resistance and compress to the point of nuclear ignition. As a result, theoretical models predict that Population 3 stars were likely huge, perhaps hundreds of times the mass of the Sun. Their size made them short-lived, dying in spectacular supernovae or collapsing directly into black holes. And their deaths seeded the cosmos with the very elements that would become the building blocks of future generations of stars, planets, and even life. But therein lies the observational challenge, population 3. Stars may have all vanished billions of years ago, their lifespans too brief for any to remain today. Their ancient light would be too dim, too diffuse to detect, unless magnified by the kind of gravitational lensing that revealed Arendelle, and even then, the alignment would have to be perfect. Still, astronomers haven't given up the James Webb Space Telescope, with its unprecedented infrared sensitivity, is now targeting deep fields of space peering farther back in time than ever before. By analyzing the chemical fingerprints of the earliest galaxies and stars, scientists hope to detect indirect evidence of population 3. Stars, perhaps by identifying supernovae with peculiar energy signatures or unusual abundance patterns in ancient gas clouds. And some are taking a different approach altogether. Stellar archaeologists, scientists who study ancient stars in the halo of our galaxy have identified ultra-metal poor stars, relics of the early cosmos that may have formed from gas enriched by a single population 3 supernova. These stars, though not population 3 themselves, may hold chemical records of their forebears. Ultimately, the discovery of a true population 3 star one completely devoid of heavy elements would be like finding the missing link in our cosmic ancestry. It would confirm our theories of early star formation and offer direct insight into how the universe transitioned from darkness to light. For now, though, population 3 remains a theoretical construct, compelling, inevitable, and yet invisible. But perhaps in some untouched corner of the sky, one still lingers, an ancient ember burning against the black. Or maybe its light is already en route, a message from the dawn of time, just waiting to be caught by our outstretched instruments. Whatever the case, we will keep searching, because in that first generation of stars lies the beginning, not just of cosmic structure, but of us. Without population 3, there would be no carbon in our cells, no oxygen in our lungs, no planets to call home. They were the architects of the universe we now inhabit. And somewhere scattered across the deep time sky, they are still whispering their story, if only we can learn how to listen. The hunt for the first stars. More than 500,000 years ago, on the island of Crete, a peculiar version of a familiar giant once roamed. Unlike their towering relatives of the Ice Age, these mammoths stood no taller than a meter. In an isolated environment with scarce resources and few predators, gigantism became maladaptive. Evolution worked its quiet transformation, and thus insular dwarfism gave rise to the pygmy mammoth. Today, their bones are rare archaeological treasures, fragments of an evolutionary past that unfolded in isolation. In many ways, astronomers today find themselves on a similar quest. They are not searching for mammoths, but for the cosmic giants that once roamed the early universe, the very first stars, the elusive population 3. These primordial titans, born of pristine hydrogen and helium, lived fast and died young. Yet just like their mammalian counterparts, there's a hypothesis that smaller variants of these ancient stars may have existed and may still be among us. If such stellar pygmies formed early and lived long enough, they may have survived to this day, quietly orbiting in the distant halo of our galaxy, masquerading as ordinary stars. This is the central idea behind the modern-day astronomical pursuit known as stellar archaeology, the search for the last survivors of the universe's first generation. When the first stars ignited their nuclear fusion, lit up a universe that had known only darkness, but they did more than shine. They changed everything. In their hot cores, these stars fused hydrogen into helium and then into heavier elements, carbon, oxygen, magnesium, and beyond. When they died in spectacular supernovae, they seeded the surrounding cosmos with the ingredients for planets, atmospheres, and eventually life. But this enrichment was swift and efficient. In just a few million years, no region of the universe remained chemically untouched. The era of pristine star formation came to a rapid end. If we wish to understand the chemical history of the cosmos, if we want to learn how galaxies evolve and how elements are forged, then we must understand these first stars. Their existence marks a turning point between two fundamentally different epochs of the universe. But there's another motivation too, one that lies beyond data and theory: curiosity. The same deep human impulse that compels archaeologists to brush dust from ancient bones drives astronomers to trace faint light back to the birth of time itself. For decades, astronomers believed the search for population 3 stars was a hopeless endeavor. Their short lives made them unlikely candidates for survival into the modern era, but this assumption rested on another, that the first stars were all massive. Newer simulations suggest that while rare, smaller first-generation stars, those with masses below the Sun may have formed in the turbulent disks of primordial star clusters. If this is true, then these low-mass population 3 stars could have lifespans longer than the current age of the universe. They might still be here, hidden among the hundreds of billions of stars in the Milky Way. This idea, however, presents a daunting observational challenge. If any of these ancient stars have survived, they are exceptionally rare. We are looking for one in a billion, perhaps 1 in 10 billion. Worse still, these stars may no longer wear their original chemical coats. Over 13 billion years, they would have drifted through enriched environments, slowly accreting heavy elements onto their surfaces, effectively disguising themselves as younger stars. So, how do we find them? The answer, once again, lies in light. Spectroscopy, the study of starlight split into its component wavelengths, reveals a stellar fingerprint. The pattern of absorption lines tells us not only what elements are present in a star's atmosphere, but also their abundances. Population 3, stars formed from primordial hydrogen and helium, should exhibit no detectable traces of heavier elements. Their spectra should be devoid of the lines associated with iron, calcium, magnesium, and other metals. But surface pollution complicates things. A truly pristine star might still show faint metal lines if it has spent billions of years drifting through enriched interstellar gas. Fortunately, not all elements are equally easy to fake. Iron, in particular, is a robust tracer. Its lines are strong and difficult to mimic with surface contamination. For this reason, many surveys begin by measuring iron content as a proxy for metallicity. Stars with unusually weak iron lines are flagged as candidates for further study. And this is where stellar archaeology becomes a delicate, labor-intensive craft. Once promising candidates are identified, astronomers obtain higher resolution spectra to measure abundances of multiple elements. They then model the expected surface pollution for stars of a given age and trajectory, subtracting the contamination to infer the star's original composition. The hope is to find a star whose spectrum, once stripped of its disguise, reveals no metals at all. In 2013, astronomers made a breakthrough. A star labeled SMM03136708 was found with no detectable iron, an astonishing find. Detailed modeling revealed that it did contain small traces of other elements, likely produced by a single low-energy supernova. This wasn't a population 3 star, but its immediate descendant. Its chemical fingerprint told the story of one predecessor, a massive star that exploded and seeded just enough material to form one solitary child. We had not found a first star, but we had found its heir. To find an actual population 3 star, we must be even more precise. We must explore the galactic regions where time has moved the slowest. The Milky Way consists of 3 major components: the disk, the bulge, and the halo. The disk, home to our Sun, is a dynamic metal-rich region teeming with young stars and ongoing star formation. The bulge concentrated in the galactic center is older but heavily obscured by dust and overcrowded with stars. The halo, by contrast, is sparsely populated and composed largely of ancient stars. It is here that astronomers have focused their search. The halo is a cosmic retirement home, a quiet space where ancient stars drift undisturbed. In this low-density environment, it is more likely that a pristine star, if one exists, could have survived intact. Yet even here, the camouflage problem remains. Polluted by time, these ancient stars may appear indistinguishable from younger ones unless we know exactly what to look for. Advanced simulations help here. By modeling how stars form and evolve in different chemical environments, astronomers can predict the detailed patterns we should expect in a true first star spectrum, even after accounting for surface contamination. The hunt then is part astronomy, part forensics. We are brushing away the cosmic dust that has settled over 13 billion years, searching for a star that was born before the universe had metals, before there were planets, before galaxies had taken shape. And as with archaeological excavations, each new find, even if not a pristine first star, provides clues. Each ancient spectrum is a relic, a piece of the puzzle. Ultimately, if we are to find a population 3 star in the Milky Way, it will not be a towering giant, but a cosmic pygmy, a small, faint relic of a bygone era. These survivors, if they exist, would rewrite our understanding of the early universe. They would confirm that even in the earliest days, the cosmos had diversity, not just in star size, but in fate. Yet the giants, the true behemoths of the cosmic dawn, may forever remain out of reach. Their light faded long ago. Their deaths seeded the cosmos with possibility, and their remnants lie scattered across time. If we are to learn their stories, we must turn not just to stellar archaeology, but to cosmic innovation, to new methods of inference, new ways of reading the scars they left behind. Their light may be gone, but their echoes in elements in stars and in us remain. Mammoths of the cosmos, tracing the giants that lit the early universe. What if one quiet evening, while scanning the familiar constellations in the night sky, you noticed a star was missing? Would you detect it one among thousands? In 2015, astronomers were confronted with this very mystery. A star once cataloged and known simply vanished. This object, designated N6946BH1, lay in a distant galaxy known as the Fireworks Galaxy. Prior to 2009, it had been a relatively unremarkable red hypergiant, roughly 25 times the mass of our Sun. But something changed. In that year, it flared dramatically, brightening to over 1 million times the Sun's luminosity. It burned with this furious intensity for several months. And then, nothing. No supernova, no fading remnant. The star had simply disappeared. Subsequent observations revealed only a faint infrared afterglow, insufficient to match any known supernova profile. Instead, astrophysicists proposed a more extraordinary explanation: the star had undergone a failed supernova. In this rare scenario, the core of the star collapses so violently that a black hole forms, directly bypassing the typical explosion and instead pulling the stellar material inward. The minimal outer layer of gas ejected just before collapse produces a faint signature, one far too dim for an ordinary supernova. If this interpretation holds true, N6946BH1 represents the first observational evidence of a black hole forming in real time without the fireworks we expected. Such an event had long been theorized to reconcile discrepancies in stellar evolutionary models. The rate at which massive stars form exceeds the observed frequency of supernovae. The implication: some stars must die more quietly than our models had anticipated. This discovery has enormous consequences. It also opens a tantalizing window into the past, offering insight into the lives and deaths of the earliest stars, the so-called Population 3 stars. These were the giants of the cosmic dawn, born from a primordial universe unpolluted by heavy elements. They were true stellar mammoths, immense, short-lived, and crucial to the evolution of everything that followed. Much like the terrestrial mammoths that once roamed Earth, these stars have left no direct descendants, and just as our knowledge of Ice Age fauna comes largely from fossilized remains and preserved DNA fragments, our understanding of Population 3 stars must be reconstructed from the traces they left behind in radiation, in gravitational ripples, and in the chemical signatures they imprinted on their surroundings. The analogy with biological mammoths extends even further. Some extinct mammoth species preserved in Arctic permafrost still retain strands of DNA and even tufts of hair. These fragments have prompted discussions of de-extinction, using modern elephants as genomic scaffolds to potentially resurrect these ancient creatures. In astronomy, the conceptual equivalent is our study of hypergiant stars like Betelgeuse or UY Scuti, modern elephants from which we infer the properties of the long-lost mammoths of the early cosmos. Despite the similarities, there is one crucial difference: we will never observe the most massive Population 3 stars directly. They have long since perished, their lives lasting only a few million years, yet they left behind unmistakable fingerprints through the radiation they emitted, the explosions they triggered, and the black holes they may have seeded. One of the most powerful tools we have to track these stellar giants is the 21-centimeter hydrogen line. Neutral hydrogen, unaffected by ionizing radiation, emits this radio wave signature due to a spin-flip transition in its electron-proton structure. But when UV photons from the first stars ionize hydrogen, they break apart the atom, eliminating the 21-centimeter signal in that region. The result is a universe peppered with holes in the hydrogen map regions where stars once blazed, leaving behind vast ionized bubbles. The cosmic map of 21 centimeter emission resembles Swiss cheese. The neutral hydrogen forms the solid cheese, and the ionized voids are the holes. Each hole represents the energetic influence of a first-generation star or black hole. The properties of these bubbles' size, shape, frequency tell us not only how many stars there were, but also how they lived and died. Mapping these bubbles is the task of advanced radio observatories like the Square Kilometer Array. Through its unprecedented sensitivity, the SKA is poised to reconstruct the timeline of the epoch of ionization, the era when the first stars and galaxies transformed the dark neutral universe into the luminous cosmos we see today. But the lives of these ancient mammoths didn't end in silence. Many died in dramatic explosions known as pair instability supernovae. These are unlike any supernova observed in the modern universe. In such stars ranging from 140 to 260 solar masses, gamma photons in the core spontaneously convert into electron-positron pairs, reducing the radiation pressure that holds the star up. This triggers a rapid collapse, followed by an explosive fusion of oxygen that completely unbinds the star. No remnant is left, not even a neutron star or black hole. All of the star's material is expelled into space, enriching its surroundings with heavy elements. Detecting such an explosion would be a cosmic milestone. The James Webb Space Telescope has the sensitivity to capture the light from these rare events, especially if the supernova is gravitationally lensed. However, such alignments are exceedingly rare. Nevertheless, even one confirmed detection would revolutionize our understanding of stellar nucleosynthesis and early cosmic evolution. There are other signs too. If two direct collapse black holes born from the collapse of massive first stars became gravitationally bound, they could merge, emitting gravitational waves detectable across the universe. Such signals are feeble due to their immense distance and age, but future missions like LISA, a space-based gravitational wave observatory, could detect them. LISA's design, 3 spacecraft separated by millions of kilometers, will allow it to detect the low-frequency waves emitted by massive black hole mergers. These mergers would provide key insights into the upper end of the population 3 mass distribution. Were these stars hundreds or even thousands of solar masses? Did they live long enough to form binaries? Did their collapse lead to the formation of the supermassive black holes now observed in the centers of galaxies? Modern astrophysics is attacking these questions from every angle, from indirect chemical signatures to high redshift supernovae, from 21 centimeter maps to gravitational wave backgrounds. The hunt is on. Each method is a different excavation tool. Some search for bone fragments, others for fossilized footprints. All strive to reconstruct the story of the earliest giants. These first stars played a pivotal role in shaping the universe. Their UV radiation ionized the intergalactic medium. Their supernovae seeded the cosmos with heavy elements. Their deaths may have spawned the first black holes, setting the stage for the growth of galaxies. They did all this in silence, in solitude, and with astonishing speed. And yet their legacy persists. The universe is forever marked by their brief but transformative existence. As we continue to observe the cosmos peering deeper into space and thus further into time, we move closer to the moment when darkness first gave way to starlight. That turning point when the universe lit its first candles remains one of the most profound in all of cosmic history. The search for the stellar mammoths is more than an astronomical pursuit. It is a journey to understand where light structure and chemical complexity began, and perhaps where our own story in its earliest form truly started.
A faint streak crosses the night sky, unnoticed at first by human eyes. In mid-October 2017, a telescope perched on a Hawaiian volcano captures it, a dim speck racing through the void. Unlike the asteroids or comets that drift in orderly paths around the sun, this object moves with reckless speed, unbound by the star's gravity. It slices through the solar system. A traveler from beyond, caught only in its fleeting exit. Astronomers, alerted by the Pan-STARRS telescope, turn their instruments toward it, but time is short. Within weeks, it fades into darkness, leaving a trail of questions. Named Oumuamua, a Hawaiian term for a messenger arriving first from afar, this object defies the familiar. Most celestial bodies in our system orbit the sun, tethered by its pull. Planets, asteroids, comets all follow predictable arcs. But Oumuamua, hurtling at 26 kilometers per second, traces a hyperbolic path, a one-way journey through our cosmic neighborhood. Its trajectory, tilted against the plane of the planets, suggests it came from deep space, perhaps another star system 30 to 80 light-years away. The light we see from it began its journey centuries ago, a snapshot of a distant past. At first, scientists assume it's a comet, an icy wanderer warmed by the sun, shedding gas and dust in a glowing tail. But no tail appears. Telescopes, including the Hubble, scan for the telltale coma, a fuzzy halo of vaporized ice, but find only silence. Perhaps an asteroid. Then, a rocky fragment cast adrift, yet its surface gleams, more reflective than the dull stones orbiting nearby. The Spitzer Space Telescope, sensitive to infrared, stares for 30 hours, seeking heat from sublimating ice. It detects nothing. Oumuamua, a few hundred meters long, slips through categories, neither comet nor asteroid. Its shape deepens the enigma. As it tumbles, its brightness surges and dips every 8 hours. A lighthouse beam in the void. This pattern, captured by ground-based observatories, reveals an object elongated, perhaps 10 times longer than wide a cosmic needle, or a flattened disk spinning chaotically. Asteroids in our system, battered into potato-like clumps, rarely stretch so far. Comets, spherical when dormant, sprout tails near the sun. Oumuamua's form, unlike anything local, hints at an origin where different forces sculpted its frame. The object's speed, faster than any natural body we've tracked, suggests a long exile, ejected from its home system perhaps by a stellar collision or planetary tug. It drifted for millions of years, battered by cosmic rays. Its surface, shiny yet scarred, bears the marks of this journey. Astronomers, racing to analyze data before it vanished, calculate its path. Entering from the direction of Lyra, near the star Vega, it swings past the sun, then exits toward Pegasus. But Vega, 25 light-years away, moved long ago. Oumuamua's origin blurs, a trail lost in the galaxy's churn. As it recedes, a stranger anomaly emerges. After rounding the sun, Oumuamua should slow, its energy sapped by gravity. Instead, it accelerates, a faint but measurable push defying Newton's laws. This non-gravitational force, detected in precise orbital tracks, baffles researchers. No visible gas jets, no dust trails explain it. The object, silent and sleek, moves as if propelled by an unseen hand. Scientists scramble, checking calculations, ruling out errors. The acceleration, though small, is real, a whisper of something new. Initial theories point to solar radiation pressure, the gentle nudge of sunlight photons. Solar sails, human-designed craft, use this force to glide through space. If Oumuamua were a thin, lightweight sheet, sunlight might push it, but its tumbling motion and lack of heat emission clash with this idea. A comet-like outgassing, where ice vaporizes into jets, seems plausible, yet the absence of a coma undermines it. The object's behavior reflective, elongated, accelerating resists every model, a puzzle carved from the stars. Astronomers, limited to weeks of observation, gather scraps of light. The Canada-France-Hawaii telescope maps its spectrum, seeking chemical clues, but finds little beyond a reddish hue, typical of irradiated surfaces. The Very Large Telescope in Chile tracks its motion, confirming its interstellar roots. By December 2017, Oumuamua is too faint, slipping beyond reach. Its brief visit, a mere glimpse, leaves humanity with data too sparse to decode its nature. Yet the questions it raises ripple outward, challenging the boundaries of what we believe possible. Oumuamua's fading light lingers in the data, a cipher from the cosmos. Its acceleration, defying gravity's pull, sparks fierce debate. Solar radiation pressure, the force of sunlight on a thin surface, seems a logical culprit. Engineers at NASA have long studied solar sails' gossamer sheets propelled by photons. If Oumuamua were such a structure, perhaps a natural flake of exotic material, sunlight could nudge it faster. But its chaotic spin, like a bottle tossed forward, suggests a denser body, not a fragile sail. Its reflectivity, brighter than local rocks, lacks the uniformity of a crafted surface. Another theory posits outgassing, like a comet's jets. When comets near the sun, their ices water, carbon dioxide sublimate, thrusting them off course. Oumuamua, passing within 1/4 the Earth-Sun distance, should have warmed enough to vent gas, yet no trace appears. The Spitzer Space Telescope, designed to catch faint emissions, sees no dust or gas. Ground-based scopes, like the Gemini Observatory, find no coma. If outgassing drives its speed, it's invisible, a ghost comet unlike any known. This absence forces scientists to rethink what materials could act so subtly. Daryl Seligman, a researcher at Cornell, proposes a radical idea: Oumuamua as a hydrogen iceberg. In the frigid depths of molecular clouds, where stars are born, hydrogen can freeze solid. Such a body, heated by the sun, might release pure hydrogen gas, undetectable by our instruments. This could explain the acceleration without a visible tail. But critics, including Harvard's Avi Loeb, counter that hydrogen ice is fragile, evaporating under starlight long before reaching us. Oumuamua, intact after eons, seems too robust for such a delicate form. Jennifer Bergner, at UC Berkeley, offers a simpler twist. Oumuamua could be water ice, bombarded by cosmic rays over millions of years. In lab experiments, such irradiation traps hydrogen gas in ice's lattice. Near a star, this ice restructures, releasing hydrogen in tiny bursts enough to push a small object without spraying dust. This dark comet, as Bergner calls it, mimics a rock but acts like a comet, its activity hidden. The theory fits known physics, using common materials, yet Oumuamua's shape and shine stretch its plausibility. Avi Loeb, a Harvard astrophysicist, challenges these natural models. Oumuamua's anomalies, its elongation, reflectivity, acceleration, don't align neatly with comets or asteroids. He suggests a bolder possibility: alien technology. A light sail, a millimeter-thick craft designed to ride starlight, could match Oumuamua's behavior. Its acceleration, driven by solar photons, needs no gas. Its shape, flat or needle-like, fits a constructed object. Loeb's calculations show a thin, reflective surface could survive interstellar travel, tumbling from a long-ago collision. The idea, published in peer-reviewed papers, ignites controversy. The scientific community splits. Some dismiss Loeb's hypothesis, citing Occam's razor-simpler explanations, like exotic ices, should come first. Others, intrigued, argue the universe's vastness makes alien artifacts plausible. Loeb, undeterred, launches the Galileo project, seeking physical evidence of extraterrestrial technology probes, satellites, relics. He critiques science's caution, urging openness to ideas that challenge dogma. Oumuamua, he argues, exposes our bias toward the familiar, a failure to imagine beyond Earth's templates. The object's shape, inferred from brightness swings, fuels this debate. If a disk, it might resemble a sail, its spin a relic of ancient forces. If a cigar-like rod, it could be a fragment of a larger structure. No telescope resolved its form, leaving room for speculation. Simulations at institutions like Caltech model its tumble, suggesting a violent ejection from its home system. A planetary disruption, where a star's gravity tears worlds apart, could launch such shards, their shapes forged in chaos. Oumuamua's surface, reddish from cosmic ray bombardment, offers few clues. Spectra from the Keck Observatory show a hue like Kuiper Belt objects, irradiated over eons, yet its reflectivity, 10 times brighter than typical asteroids, hints at a smoother or icier composition. The lack of infrared glow puzzles researchers. Comets, warming near the sun, emit heat. Oumuamua's silence suggests a cold, inert body or something engineered to absorb little energy. Each datum, meticulously gathered, deepens the riddle. The acceleration, tracked by the European Southern Observatory, remains the crux. Its push, equivalent to a feather's nudge, grows stronger as Oumuamua recedes. This pattern matches solar radiation pressure, which weakens with distance, but not outgassing, which spikes near the sun. Loeb's sail fits this curve, yet natural theories persist. Nitrogen ice, like Pluto's surface, could sublimate invisibly, but its rarity in interstellar space strains credulity. Each hypothesis, tested against sparse data, falters under scrutiny. Astronomers turn inward, seeking analogs in our system. Seligman's team scans near-Earth asteroids, finding 6 with subtle non-gravitational shifts. These objects, small and rocky, lack cometary tails but move as if pushed. 1998, KY26, a 30-meter speck, spins every 10 minutes. JAXA's Hayabusa 2, fresh from Ryugu, targets it for a 2030 flyby. If it vents hidden gas, it could confirm the dark comet theory, linking Oumuamua to local cousins. The mission, a chance to touch the puzzle, carries humanity's hope for answers. These dark comets, if real, suggest Oumuamua wasn't unique. The solar system, once a closed bubble, emerges as a crossroads. Jupiter's gravity snares passing objects, some lingering in odd orbits. Asteroid 514107, Kaipioa Wila, locked in resonance with Jupiter, may be interstellar, its chemistry alien. Comets like Hale-Bopp, rich in carbon monoxide, hint at distant origins. Each discovery, catalogued by observatories like Arecibo, reveals a galaxy where wanderers are common. The galaxy's highways hum with travelers, and Oumuamua was not alone. In August 2019, Gennady Borisov, an amateur astronomer in Crimea, spots another intruder, named 2I Borisov. It blazes through the solar system, a comet with a glowing coma and a tail stretching tens of thousands of kilometers. Unlike Oumuamua's silence, Borisov announces itself, venting gas and dust as it nears the sun. Its carbon monoxide, abundant beyond local comets, points to a birthplace in a colder stellar nursery, perhaps 100 light-years away. Its hyperbolic path, like Oumuamua's, confirms an interstellar origin, entering from Hercules and exiting toward Telescopium. Telescopes, including the Swift Observatory, track its outgassing, a textbook comet born under another star, yet its contrast with Oumuamua sharpens the mystery. One visitor, loud and bright, fits known physics; the other, sleek and silent, defies it. Together, they suggest a galaxy teeming with diverse wanderers, some visible, others elusive. Estimates from the University of Hawaii suggest thousands of interstellar objects cross Neptune's orbit daily, most too small or faint to see. The solar system, a speck in the Milky Way's spiral, lies on a busy route. Massive planets like Jupiter act as nets, temporarily capturing passers-by. Objects like Comet Makemake, with alien chemistries, may be relics of such encounters. These findings, published in Nature, reshape our view, casting the sun's domain as a galactic interchange. Oumuamua's acceleration, still unexplained, drives the search for answers. Bergner's dark comet theory gains traction, as lab experiments mimic its behavior. Water ice, irradiated for eons, releases hydrogen in controlled bursts, matching Oumuamua's push, but its shape 10-to-1 elongation challenges this model. Simulations at MIT suggest a natural body stretched by tidal forces near a star, yet no known process yields such extremes. Loeb's sail, a constructed artifact, remains a shadow hypothesis, unprovable without more data. The object's origin, traced by supercomputers at Oxford, remains elusive. Its path, rewound through the galaxy's gravitational maze, points nowhere precise. Stars in Lyra, like Vega, drift too fast to align with Oumuamua's past. Clusters like the Pleiades, 50 light-years distant, offer possible birthplaces, but simulations yield no matches. The object, drifting for hundreds of millions of years, erases its tracks, its surface a palimpsest of cosmic weathering. Its journey, solitary and vast, began before humanity's first fires. Project Lyra, launched by researchers in London, dreams of pursuit, a spacecraft, using Jupiter's gravity and a solar slingshot, could reach 70 kilometers per second, catching Oumuamua by 2048, launching between 2030 and 2033. It would brave the sun's heat, navigating a needle's eye in deep space. Yet the object, now a faint speck, poses a challenge. Its tumble, unpredictable after decades, complicates targeting. The mission, costing billions, bets on a single chance to touch the unknown. Closer to home, the Vera Rubin Observatory in Chile prepares for the next visitor, set to scan the sky in 2025. Its legacy, survey of space and time, will map every flicker, catching dozens of interstellar objects yearly. Unlike Oumuamua, spotted weeks after its closest approach, future travelers may be seen months ahead, allowing probes to intercept them. The European Space Agency's Comet Interceptor, launching in 2029, waits in space, ready to chase an incoming comet or alien object, its instruments primed for close study. These missions, born from Oumuamua's wake, mark a shift. Humanity, once reactive, builds tools to anticipate. The Rubin's 10-year survey, imaging the sky every 3 nights, will catalog larger, slower visitors, their paths traceable. Interceptor's flexibility, orbiting a stable point, lets it pivot to new targets. Together, they promise a harvest of data, revealing how often the galaxy sends messengers and what they carry: ice, rock, or something stranger. Its acceleration, if driven by radiation pressure, inspires new sail designs at institutes like Caltech. If a dark comet, it redefines cometary physics, prompting studies of local asteroids. The 1998 KY-26 flyby, planned by JAXA, tests this theory. Its data a bridge to Oumuamua's nature. If alien, it challenges our search for life, pushing projects like SETI to scan for physical artifacts, not just signals. The galaxy, a spiral of 200 billion stars, hides countless such objects. Oumuamua's path, crossing ours by chance, suggests others wait unseen. The local bubble, a 1,000 light-year cavity around the sun, formed by ancient supernovae, may channel these travelers, its hot gas a highway for debris. Ambrosita's X-ray maps, from orbits beyond Earth's atmosphere, hint at tunnels linking such bubbles, a galactic network where Oumuamua once roamed. Oumuamua's trail, now cold, stretches toward Pegasus, a speck lost in the void. Its brief passage, a mere month in our skies, rewrites our cosmic map. Borisov's arrival, 2 years later, confirms the galaxy's restlessness. Its coma, glowing with carbon monoxide, spans 50,000 kilometers. A beacon from a star system colder than ours, tracked by the Chandra X-ray Observatory. Its outgassing mirrors local comets, yet its chemistry rich in alien ices sets it apart. These two visitors, one cryptic, one open, hint at a spectrum of interstellar wanderers. The dark comet theory, tested by local asteroids, gains ground. 1998 KY26, a 30-meter rock, spins furiously, its orbit nudged by unseen forces. Hayabusa 2's flyby, planned for 2030, will probe its surface, seeking hydrogen trapped in irradiated ice. If confirmed, dark comets could number thousands in our system, their subtle pushes reshaping orbital models. The Pan-STARRS survey, which found Oumuamua, now hunts these ghosts. Its data-feeding algorithms at the University of Arizona, Loeb's alien hypothesis, though divisive, spurs innovation. The Galileo project, funded privately, deploys telescopes to scan for artificial objects, probes, sails, or debris. Its arrays, dotting observatories in New Mexico, seek infrared signatures of technology, a shift from SETI's radio focus. Loeb's book, Extraterrestrial, argues Oumuamua's anomalies shape, shine, acceleration fit a crafted relic, perhaps a derelict probe from a civilization long gone. Critics, citing natural ices, demand proof, but the debate fuels curiosity. Oumuamua's acceleration, a tenth of a millimeter per second squared, remains the pivot. Models at the Max Planck Institute test exotic ice's methane, carbon monoxide sublimating, invisibly. None fully match the data. Solar radiation pressure, requiring a thin, reflective body, aligns better, yet Oumuamua's density, inferred from its tumble, suggests a solid core. The tension between theories drives experiments, from ice irradiation at CERN to sail prototypes at JPL. Each test, grounded in Oumuamua's clues, pushes science forward. The object's shape, a 10-to-1 ratio, haunts researchers. Tidal forces, stretching a body near a star, could form such needles, but require extreme conditions. Simulations at Stanford model a planet shredded by a white dwarf, launching elongated shards. Oumuamua, if such a fragment, carries a story of stellar violence. Alternatively, a flat disk, spinning like a coin, fits a sail's profile, its tumble a scar of ancient impacts. Without images, both shapes live in equations, a duality unresolved. The Rubin Observatory, its 8-meter mirror scanning Chile's skies, will spot them monthly, its deep exposures catching faint glints. Comet Interceptor, parked at a Lagrange point, awaits a slow-moving target, its spectrometers ready to parse alien ices. These tools, inspired by Oumuamua's escape, aim to catch travelers early, orbiting them for months. Such missions, planned by ESA and NASA, could sample surfaces, revealing compositions forged under distant suns. Its solar Obi-Earth maneuver, firing engines near the sun, demands precision. A probe, shielded against solar heat, would race past Oumuamua, imaging its surface at 20 kilometers per second. The data, beamed back by 2050, could show craters, fractures, or artificial seams. The mission's risk, a decades-long gamble, reflects humanity's drive to grasp the fleeting, a quest born in Oumuamua's wake. Formed 10 million years ago by supernovae, it spans 1,000 light-years, its edges birthing stars. Oumuamua, passing through, may have ridden its currents, guided by plasma tunnels mapped by Erosita. These channels, linking bubbles across the galaxy, suggest a cosmic web where objects drift. Borisov, too, navigated this network, its path a thread in the Milky Way's tapestry. Humanity's watch extends beyond Oumuamua. Ancient Polynesians, navigating by stars, saw the same sky, unaware of its travelers. Today, amateurs with 10-inch scopes contribute to surveys, their data vital. The American Association of Variable Star Observers, logging Oumuamua's brightness, feeds global models. This blend of citizen and professional science, amplified by AI, scans for the next visitor, a collective effort to meet the galaxy's messengers. The galaxy itself, 200 billion stars strong, pulses with motion. Oumuamua's path, a chance crossing, mirrors countless others. Kaiapawawela, orbiting backward with Jupiter, may be a captured wanderer, its orbit a fossil of interstellar exchange. Comets like Hyakutake, their ice is alien, reinforce this flow. Each object, studied by telescopes like ALMA, reveals a solar system porous to the stars, a stage for cosmic encounters. Oumuamua drifts toward Pegasus, a silent speck in the galaxy's depths. Its passage, brief and baffling, leaves a trail of light and questions. Borisov, its cometary cousin, blazed through 2 years later, a reminder of the galaxy's restless traffic. Together, they reveal a solar system not isolated, but woven into the Milky Way's fabric, a crossroads where alien objects pass daily. The Rubin Observatory and Comet Interceptor, poised for action, stand ready to greet the next, their lenses and probes a bridge to the unknown. The object's acceleration, a faint push against the sun's pull, anchors the mystery. Bergner's dark comet, water ice venting invisible hydrogen, offers a natural path, grounded in lab tests. Loeb's light sail, a whisper of alien craft, challenges orthodoxy, urging science to stretch. Between them lie theories of exotic ice's nitrogen, methane each tested, each flawed. Oumuamua's shape, elongated or flat, and its reflective surface defy easy answers, a riddle etched in starlight. The 1998 KY-26 flyby, probing local dark comets, may clarify its nature, linking the alien to the familiar. Project Lyra's dream, chasing Oumuamua to 2048, embodies humanity's resolve. Its solar slingshot, a fiery gamble, aims to capture images of a tumbling relic, be it rock or relic. The mission, though distant, echoes the Vera Rubin's vigilance, scanning for new travelers. These efforts, born from a single visitor, reshape astronomy, turning our gaze from static stars to dynamic intruders. The local bubble, its tunnels guiding such objects, frames this quest, a galactic stage where Oumuamua played its part. The galaxy's scale, 200 billion stars across 100,000 light-years, dwarfs our system. Oumuamua, ejected from an unknown star, drifted for eons, its origin lost in stellar orbits. Vega, once a candidate, drifts too far. Clusters like the Hyades offer no firm link. Yet its journey, scarred by cosmic rays, speaks of a universe in motion, where planets shatter and stars collide. Borisov, Kaiapawawela, and others trace similar paths. Their chemistry is a record of distant worlds. Humanity's response, from Hawaiian telescopes to global observatories, shows a species awake to the cosmos. Ancient Sumerians, charting stars 5,000 years ago, saw the same sky, their clay tablets marking time. Today, we parse light with silicon, our data a modern epic. Amateurs, logging Oumuamua's flickers, join professionals at Keck and Hubble, a shared pursuit. This unity, sparked by a fleeting visitor, drives missions like Interceptor, ready to touch the next messenger. Its anomalies' speed, shape, acceleration force science to question assumptions. Dark comets, if real, redefine our system's boundaries. A sail, if true, redefines life's reach. Each theory, from Seligman's ice to Loeb's craft, pushes boundaries, sparking experiments and debates. The Galileo Project, scanning for artifacts, and Rubin's Sky Survey, hunting wanderers, carry this forward. a search for truths beyond our templates. The solar system, once a closed orbit, emerges as a galactic hub. Comets from the Oort cloud, nudged by passing stars, link us to the Milky Way's churn. The local bubble, carved by ancient explosions, channels these flows, its plasma tunnels a cosmic road. Oumuamua, Borisov, and future visitors ride these currents, their paths a story of creation and chaos. Humanity, watching from a blue speck, meets them with wonder, our tools and dreams aimed at the stars.